Jai Jagannath. So, welcome to lecture number 3 of capacitance. So, in the last class, we had discussed the polarization of dielectric medium inside the capacitor. So, I want to find what is the dielectric constant value for metal. So, for an insulating medium, for air, what is the dielectric constant? So, for air, the dielectric constant is equal to 1. Remember, dielectric constant is also equal to relative permittivity. So, now we will find what is the dielectric constant for a metal. So, you see the metal, suppose you see this is a capacitor. Let us say the area of the plate is A, and in between these two capacitor, instead of a dielectric medium, I will keep a metallic plate. So keep a metallic sheet in between these two plates. So what is the logic you see? If this is the positive charge plate, this is the negative charge plate, what will happen? An electric field will be developed inside the plate. That electric field is equal to E naught. But due to this electric field, the dipole will be polarized, and here all the negative charge will come to this side and all the positive charge will come to this side. So this has been explained in the last class. If you have not seen that video, please refer to that video, then you come to this. So now you see this is positive, this is negative plate, negative charge developed in the metallic sheet. Now due to this positive and negative, an electric field will be developed. So that electric field is called EI, induced electric field. Then what is the net electric field? Net electric field is equal to, so this is E naught, this is EI, so net electric field is equal to this. So this is the net electric field intensity, which is nothing but E naught by K. So in the last class we have discussed in details. So now you see, so what is the net electric field intensity inside the plate? So net electric field intensity is equal to E naught minus EI. So that net electric field intensity is nothing but E naught by K. But we know, using Gauss law, we have already proved that electric field inside metallic conductor, inside metallic conductor is equal to 0. So that implied the net electric field intensity, which is equal to E naught by K, that is equal to 0. So that implied K is equal to E naught by 0. So something by 0 is infinite. So we can say the what is the value of K for metal? So K for metal is equal to infinite. Then what is the charge induced in this metallic sheet inside the capacitor? So now we know the relation between the surface charge density due to induced charge is equal to the surface charge density due to given charge into 1 minus 1 by K. So in this case, K value is equal to infinite. If we put K is equal to infinite, 1 by infinite is 0, that implies sigma I is equal to sigma. So same amount of charge is induced. That means same amount of charge is induced across the metal as that of charge on the plate of the capacitor. That means if sigma I is equal to sigma, we can say Qi is equal to Q. So this Qi is nothing but charge induced in metallic sheet is equal to charge given on the surface of capacitor. But for any dielectric other than this metallic sheet, the sigma I, surface charge density due to induced charge, is less than sigma, or you can say Qi is less than Q. So this is a test or understanding question. A vacuum is there inside a capacitor. Suppose you take this is a capacitor. Inside this capacitor there is vacuum. You know for vacuum what is the relative permittivity or dielectric constant? That is 1. Now let us say the charge is initially it is Q and this is minus Q, and so initially the capacitance was E or C. Let us say potential difference is V, so C is equal to Q by V. Okay. Now question is, if charge on each conductor is doubled, what happens to the capacitor? So I have already discussed in the theory, if charge is doubled, that means the new charge Q dash is equal to 2Q, then automatically the new voltage will be also double. If charge is double, voltage will be double, then what is the capacitance? Capacitance is equal to Q dash by V dash. So that is equal to 2Q by 2V, which is equal to Q by V. So Q by V is nothing but C. That means the capacitor, new capacitance will be same as that of original capacitance. That means our answer is remains same. Now example 24.3, here you have to derive the capacitance of a spherical capacitor. Okay. So what is a capacitor? I had told the two plates separated by thin layer of dielectric forms a capacitor. So here, since it is spherical capacitor, the two plates are of spherical in nature. That means if I take two spheres, so this is your, let us say, this is your A sphere, this is your B sphere. So there are two plates. Two plates are of spherical in nature. That's why it is called spherical capacitor. Now see, to form the capacitors, this outer sphere must be hollow. So the outermost sphere must be hollow, but the inner sphere may be hollow or may be solid sphere. Why? Because the outermost sphere must be hollow, so that in between this A sphere and B sphere you will put some dielectric medium, either air or rubber or plastic or polymer, whatever, or paper. So this is your dielectric medium. So now let us say the radius of this inner sphere is RA and the radius of outer sphere is equal to RB. Okay, I am taking the inner sphere is small r and the outer sphere radius is capital R. Okay, so now how will you find the capacitance? You see, suppose we are giving a charge of plus Q to the surface of A sphere. Then what will happen? If the charge on the outer surface of the inner sphere is plus Q, then it will induce a charge of minus Q. It will induce a charge of minus Q on the inner surface of the outer sphere. So that things we have already discussed. And since we are giving the charge to A body, not to A body, so body B is electrically neutral. So now due to induction of the charge of A on B, so there is minus Q charge is developed. But B sphere is electrically neutral. So definitely on the outer surface it will be plus Q charge. Outer surface it will be plus Q charge. But I have already told for any capacitor the second plate out of two plates, the second plate must be connected to earth to increase the capacitance. So I will connect the earth. If I will connect the earth, what will happen? This outer charge, that is plus Q, will move towards the earth surface. Okay, only negative charge will be there. Why? This negative charge will be bounded by this positive charge. So this is the logic. That means here there are two spherical conductors separated by a dielectric medium. One plate is a positive charge, another plate is negative charge. Okay. So now mind it, if there is no connection of earth shown in the figure, you have to assume it is already connected to the earth. So this is the logic of the capacitor. Now we will find what is the capacitance between these two plates. So first we will find what is potential at a point, that is point lying on the surface of the inner sphere. So what is potential at A? There are two charges, one is plus Q, another is minus Q. So I can write potential at A is equal to potential due to inner sphere, charge at inner sphere, plus potential due to outer sphere, charge of outer sphere. Okay. So now we see for the inner sphere, what is the charge? Plus Q. And what is the potential at this surface point due to a charge Q? We know K Q by its radius is R plus. And here you see this point is the internal point for the outer sphere. So we know for internal point the potential on the surface is same as a that of internal point. So I have to find the potential at A point. So potential at A due to the outer sphere is nothing but K, and what is the charge on the outer sphere? Minus Q. And what is the radius of outer sphere? R. So this is the potential on the surface of the outer sphere. And that potential is also equal to the potential at the internal point due to this outer sphere. So now you can write, so here common is KQ 1 by R minus 1 by R, that is equal to KQ R minus R divided by R into R. So this is the potential at which point? A point. So I am writing potential at A point is equal to this. Then what is potential at B? Since it is connected to earth, the earth potential is 0, so VB is equal to 0. So now what is the potential difference between two conductor? The potential difference is nothing but VA minus VB, which is equal to VA is equal to KQ R minus R divided by small r into capital R. This is VA minus VB. So but VA minus VB is nothing but potential difference. VA minus VB is nothing but potential difference. So this potential difference is equal to KQ R minus R by small r into R. But we know what is the capacitance. Capacitance is nothing but charge per potential difference, charge per unit potential difference, that is Q by V. So that implied Q by V is equal to small r by K into R minus R. But what is K? K is equal to 1 by 4 pi epsilon naught epsilon r. So if you take K is equal to 1 by 4 pi epsilon naught epsilon r, then I can write 4 pi epsilon naught epsilon r small r into capital R divided by capital R minus small r. So this is the capacitance of a spherical capacitor formula. I think it is clear. Okay. So this is the capacitance of a spherical capacitor. Now if you take an isolated spherical conductor, that means only one conductor is there. Okay. So I am writing here, you see, for isolated sphere means only which sphere is present? Only first sphere, that is only a sphere is there. Only a sphere is present. But we know for capacitor there must be two plates. So it is so for isolated sphere, if A is the spherical conductor, then other conductor, then B conductor is what? It is earth. Okay. So for isolated conductor, the second plate is treated as earth. But what is the radius of earth? It is 6400 km, which is very greater than the radius of a normal sphere. So we can say the radius of earth, it tends to infinite. If so, then what is the capacitance formula? So we have known 4 pi epsilon naught epsilon r small r into capital R by R minus R. This is the capacitance of a spherical capacitor. If for isolated spherical conductor this r tends to infinite, now what you will do, you just divide capital R in numerator as well as denominator. So if you divide capital R in numerator, it is will be R divided by R is equal to 1 minus small r by R. But this R tends to what? Infinite. Something by infinite is 0. So that means capacitance of an isolated spherical conductor is equal to 4 pi epsilon naught epsilon r into radius of that conductor. It is already I have derived in the previous lecture. So next example 24.4. 24.4. Here you have to derive capacitance of cylindrical capacitor. So if the two plates are of cylindrical nature, then it is called cylindrical capacitor. So here there are two cylinders, one is inner cylinder, another is outer cylinder. Both are concentric cylinder, that is their axis of both are same. Axis of both are same. And similar to the spherical capacitor, the outer cylinder must be hollow and the inner cylinder may be hollow or may be solid sphere, so that we can keep a dielectric medium in between two cylinders. So the second cylinder is always connected to the earth to increase its capacitance. I have already explained. So now you see we are giving a positive charge to the inner cylinder. All the charge will be distributed on the surface. Let lambda is the charge density. Lambda is the charge density on this line. Okay, on this line. So now we have to find what is the potential difference between A point and B point. So according to the electrostatic potential concept, we know VA minus VB is equal to line integral of E dot dl from A point to B point. It is already explained. So VA minus VB is equal to this. Okay. So that is equal to integration of what is E? E is the electric field intensity. So we are moving from A point to B point. So direction is of electric field is from A to B, and we are moving along same direction. So E dot dl is nothing but E dl cos 0. That is A to B. So that implied VA is equal to VA, but VB is equal to what? 0. Because the outer cylinder is connected to the earth. The potential of earth is 0. So potential of B is also 0. That is equal to integration of E. So we have already derived the electric field intensity due to a cylindrical conductor, which is nothing but lambda by 2 pi epsilon naught r into, instead of dl we will write in a radial line, instead of dl we will write dr. So here we are moving from which point to which point? A point to B point. So at A point, what is the radius? Radius is RA. At B point, what is the radius? Radius is RB. So now you have to integrate. So here that implied VA is equal to lambda by 2 pi epsilon naught is a constant. What is the integration of 1 by r? dr. You know it is ln r. So lower limit is RA, upper limit is RB. So just integrate this and put the upper limit and lower limit. You will get lambda by 2 pi epsilon naught ln RB minus ln RA. So I am writing for your easy clarification ln RB minus ln RA. So that is equal to lambda by 2 pi epsilon naught. Ln x minus ln y is equal to ln x by ln y. So ln RB by RA. Now see, so VA is equal to this much. Okay. So what is, so VA is equal to lambda. What is lambda? It is the total charge distributed per unit length. That is lambda is equal to Q by L. If the length of the cylinder is L and total charge given on the surface is equal to Q, so Q by L is the lambda. So VA is equal to lambda is Q by 2L into 1 by 2 pi epsilon naught ln Rb by Ra. So that implied we have to find capacitance. Capacitance is nothing but Q by V. So from this expression you write Q by V is equal to what? L into 2 pi epsilon naught divided by ln Rb by ln Ra. Ln Rb by Ra. So that implied C by L is equal to what? 2 pi epsilon naught by ln Rb by Ra. So what is C by L? So capacitance per unit length. So if the unit of capacitance is farad, length is meter, so whatever you will get the result, this will be in terms of farad per meter. So this is the expression of the capacitance in a cylindrical. So why it is required actually? Why it is required to calculate the capacitance? You see, in the electrical transmission wire, so there are various cable. Okay, so suppose this is your R phase, this is Y phase, this is B phase, all the lines are the transmission line. So the transmission line is also just like a cylindrical in nature. So here in between these two transmission line, there is a capacitance. So we have to design in such a way that there's the space between these two line conductor must behave as a dielectric medium. If the dielectric you will lose, what will happen? There will be leakage current, so which will be danger. So according to that, we have to design the capacitance of the cylindrical conductor, and according to that, we have to take the transmission line. So now this is important question. There are always this question comes in the exam. Derive the energy stored by capacitor and hence energy density. So we know the purpose of capacitor. Capacitor stores charge as well as energy. So what is the formula of energy stored by a capacitor? Now see. Suppose you see this is a switch. Okay. So initially this capacitor is not charged. So at t is equal to 0, what is the charge across capacitor? It is 0. And what is the potential difference across the capacitor? V is equal to Q by C. So Q is equal to 0, so potential difference is also 0. But what is the capacitance? Capacitance is equal to C. Now, if we close the switch, after some time t is equal to t, at any instant t, let the charge across the capacitor is Q, and potential difference is nothing but Q by C, and capacitance always remains same, that is C. Now, when the capacitor is charged fully, that is at t tends to infinite, the total charge stored in the capacitor is maximum, that maximum charge is say Q. And the potential difference across the capacitor is equal to the supplied voltage, that is the voltage across the capacitor is maximum, that is V. And what is the capacitance? Capacitance is equal to C. And we can write this V is equal to what? Q by C. This V, the voltage across the capacitor, you can write here. The voltage across capacitor will be V, which is equal to maximum charge by capacitance. Okay. So from this you can say Q is equal to CV. So Q is the maximum charge. V is the maximum voltage developed across the capacitor, which is equal to the supplied voltage. C is the capacitance. Now, so what is the logic? How the energy is stored? You see, initially when the switch is open, there is no charge. If there is no charge, there is no work done by the source. So this is called source. And this source is called EMF, electromotive force. Okay, so this is the source. Now, so initially there is no work. So at t is equal to 0, no work is done by source. But when at t is equal to t time, the charge across the capacitor is already, this is plus Q, this is minus Q. At what time? At t is equal to t. At that time, there is a potential difference across the capacitor, which is equal to V. So now the battery tries to send dq amount of charge after this Q charge. That means already capacitor stores of what charge? Q. So after that, battery tries to send dq amount of charge. So in that case, what will happen? So this q already exists charge will repel this dq charge supplied by the battery. So to against the repulsive force produced by this existing charge, the battery or the source has to do some work. So I am writing to send dq charge by source against the repulsive force against the repulsive force by existing charge by existing charge. Source has to do some work. Source has to do some work. Since charge sending amount is very small, that is dq, so work done is also very small, that is dw. And we know dw is nothing but v into dq. Because you know the potential difference between 2 points is equal to amount of work done by bringing a unit charge from one point to another. So v is equal to dw by dq, or dw is equal to v dq. Okay, but that implied what is v? The potential difference across the capacitor at any instant is equal to q by c. So v is equal to q by c into dq is equal to dw. Okay, so now we have to find the total work done by the source to send the charge from 0 to maximum value. So total work done by source to send charge from 0 to maximum is equal to w is equal to integration of dw. So when the charge is equal to 0, so you see dw is nothing but what? Q by c dq. So when charge is initially 0, work done is 0. When charge is maximum, work done is equal to maximum. So that means we will integrate. Here charge is variable. So initially charge was 0 and finally it is maximum. So that implied W is equal to 1 by C. C is called capacitance, that is constant. So Q dQ integration. What is Q dQ integration? Q square by 2. Lower limit 0, upper limit Q. So that implied work done is equal to 1 Q square. So put the lower limit and upper limit. So upper limit is equal to Q square minus lower limit 0 square. So Q square by 2C is the work done by the source to send the charge from 0 to maximum, that is Q. Okay, and you know, every time I have told, if anybody is doing work against any force, so that amount of work done will be stored in the form of potential energy. Because here the charge motion, here the battery is sending the charge with constant speed. That means kinetic energy is not changing. Only the potential energy will change. So the total amount of work done by the source against the repulsive force is equal to Q square by 2C, and this amount of work done will be equal to potential energy stored across the capacitance. So U is equal to what? Potential energy stored in capacitor. And this energy is which energy? This is electrical energy. Why electrical energy? Because inside the plate there is electric field. Inside this space there is electric field. So whatever energy is stored, that is in the form of electrical energy. So we can write the total work done W is equal to Q square by 2C. It is which energy? Electrical energy. Electrical energy. Inside what? Inside the dielectric. Inside the dielectric of capacitor. That means energy is stored inside the dielectric of the capacitor. So, and this work done is nothing but your potential energy, electrical energy. What is the formula? Q square by 2C. And we know Q is equal to C into V. So Q square is equal to CV square by 2C. So C square and C cancel, so it is half CV square. This is the potential energy in terms of capacitance and voltage. This is the potential energy in terms of charge and capacitance. Also we know that half CV square is nothing but CV into V. That is equal to half CV. CV is equal to total charge Q into V. So this is the energy stored in terms of charge and potential. Okay, so you have to remember this formula, this formula, this formula, all are interrelated formula. This is the energy stored. Now we will find what is the energy density. What is the energy density? So energy is stored inside the dielectric medium. Then what is energy density? So energy density is nothing but energy stored per unit volume. Energy stored per unit volume. So what is energy stored? That is half CV square. Then volume. Suppose you take a parallel plate capacitor. This is a parallel plate capacitor. So what is the distance of separation? D. What is the area of the plate? A. So what is the volume of the dielectric medium inside the plate? You see, area into D. Area into D. Suppose you see, this is my plate, this is my this two hand is my two parallel plate. So the area of the plate is A. Distance of separation is D. Then what is the volume of dielectric inside these two plate? Area into distance. So volume is equal to area into distance. Okay. So this is your energy density. But what is the value of capacitance? We have discussed now. Half C. C is equal to, for parallel plate capacitor, I can write it is epsilon A by D. Epsilon is nothing but, epsilon is equal to what? Epsilon naught into epsilon R. So capacitance formula is equal to epsilon A by D into V square divided by A into D. So that is equal to half epsilon A cancel, we will get V square by D square. That is equal to half epsilon, that is V by D whole square. So if the potential difference between the two plates is V, distance of separation is D, then what is the value of V by D? We know the V by D is nothing but electric field intensity. So this electric field intensity inside the two plates is constant. Why constant? Because we are taking the distance of separation between two plates is very small. Okay, comparing to the area. That's why electric field always remains uniform, which is equal to V by D. Then what is energy density? So that implied energy density is equal to the energy per volume. Energy per volume is equal to what? Half epsilon V by D is nothing but E, so E square. So this is the expression of energy density. So which is equal to half, what is epsilon? It is epsilon naught, epsilon R into E square. So what is the unit of this? Energy is equal to joule, then volume is meter cube. So energy density unit is joule per meter cube. So the energy stored by the capacitor depends upon relative permittivity. For air capacitance, epsilon R is 1. For any other capacitance, the epsilon R is large. So we can say energy density is directly proportional to what? Epsilon R. Now see, this is an interesting question. We know, suppose this is a capacitor. So this plate is plus Q charge, this is minus Q charge. If the potential difference between these two plates is V, then what is the capacitance formula? Q by V. So here this is plus Q, this is minus Q. So we take the charge is Q, C is equal to Q by V. But here what happens we see. This plate is having plus 5 coulomb charge. This plate is having 0 coulomb charge. In that case, what is the formula of capacitance? You cannot write 5 or you cannot write 0. But because here Q and Q, similar, same charge is there. So you can write C is equal to Q by V. But here what is the capacitance? So capacitance in this case is equal to, how will you find? So you know the capacitance is equal to Q by V. But what is the value of Q? So what will write here? Let us say this is Q1 which is equal to 5 coulomb. This is your Q2, which is equal to 0 coulomb. So this Q is nothing but Q1 minus Q2 divided by 2 divided by voltage. So here it is 5 coulomb minus 0. 5 minus 0 divided by 2 by V. So what is V? V in this example it is given 100 volt. So that is equal to 2.5 by 100. So if you multiply 10 in the numerator and denominator, it will be what? 25 millifarad. So this is the capacitance. Now here what is the value of capacitance? You see, so here 10 coulomb charge. So Q1 is equal to 10 coulomb, Q2 is equal to 6 coulomb. So this capacitance is nothing but Q by V. So how will you take the charge here? Q is nothing but what? Q1 minus Q2 divided by 2 divided by V. So what is Q1? Q1 is equal to 10 minus Q2 is equal to 6 divided by 2 divided by 100, that is equal to 10 minus 6, that is 4 by 2, 2 by 100. So that is equal to 20 millifarad. Similarly, here what is the capacitance? Capacitance is equal to Q1 is 10 minus Q2, it is minus 6 divided by 2. This is your charge divided by voltage. So that is equal to 10 plus 6, 16 by 2, 8. So 80 millifarad. Okay, so this is about the charge. How that if there are two different charges, so how can you find the charge capacitance? So in the next class, we will start with the combination of capacitor. Till that, you enjoy. Okay, bye.